all integers n²+2n is even. So what should we do when we look at this problem? When something says for all integers, what should go through your mind is that there's only really two types of integers. There are odd and there are even, which means that when we're trying to look at this problem, we need to look at both sides. There's two cases. So let's think of some examples for each case. Let's first start with even, right? Let's plug in some even n and see if the answer is in fact even. So let's try 0, right? 0 squared plus 2 times 0 is 0. So yeah, that's in fact even. Okay, let's try one more even number. Let's try 2. 2 squared plus 2 times 2 is going to equal to 4 plus 4, which is 8, and that's even. Okay, so when the integers of n are even, this statement is true. Now let's try the other side, the odd side. The first odd number you should try is probably 1, so let's give 1 a shot. 1 squared plus 2 times 1, this is going to equal to 3. Okay, we found a problem. There are some integers n, for example 1, where n²+2n is not even. As you can see here, it's equal to 3 when n is equal to 1. Let's just do one more odd number to make sure. Let's try 3. So 3 squared plus 2 times 3. This is going to be equal to 9 plus 6, which is going to be equal to 15, which is also not even. Okay, so this statement is false. And all we need to disprove it is just look at one of these cases where it's not true. And we're going to use the very simple case of 1. So how do we prove a statement is false? Well, we start by writing out its negation. When we know that this is not true, we're going to instead prove the negation is true. So what is the negation of this statement? So a negation of for all is going to be a there exists. So we're going to write down there do exist integers n such that n²+2n is not even. Again, if you don't like this, you could just replace the not even by saying odd. What do we do now? Now we need to show that to say this is false, this red statement must be true. So let's prove the red statement. And we've kind of already did the bulk of the work by finding an n, that there isn't exactly an n where this statement is true. So let's just write that down. So how do we start this? We say, for example, comma, let n equal 1. Okay, great. Or we'll be a little more precise. Let n be an integer and n equal to 1. So, I mean, you don't really need this first part, but we're just going to say n is an integer and it's equal to 1. Full stop. Then n² + 2n is going to equal to 1 squared plus 2 times 1, which is going to equal to 3. Great. And here we can say 3 is odd. So therefore, the negation of the statement is true, comma, which means the original statement is false. Okay. Great, so we've proven that this statement is false. If you want to be more precise, you can maybe try and show that 3 doesn't fit the definition of even. If you want to do that, this is how you would do that. So you would keep this sentence here, this conclusion, but right before it, you would put down 3 is not even, because if 3 is equal to 2k plus 1 for some integer k, k is going to equal to, take away 1 from both sides, that's 2. Oh, I'm sorry. We're going to say this is odd, my bad. I'll write right below this what you would say if it's even. 3 is odd because for some integer k, where k is equal to 1 in this case, right? You can also just say the opposite. Proof by contradiction, a really light and informal proof, is not even because for the definition, you can add this for definition part up here too, but again, what I'm writing here is unnecessary. For the definition of even, 3 equals to 2k for some integer k, but k equals to 3 over 2 when 3 is equal to 2k, and 3 over 2 is not an integer, so 3 cannot be even. And then you would add the conclusion I wrote earlier.